Chapter 8, Sections 1 to 3, Basic Bipolar Junction Transistor Amplifiers. One thing to keep in mind as we go through talking about amplifiers is that capacitors appear as open to DC sources and as short to AC sources. This will greatly simplify our use later on when we talk about analyzing an amplifier. So first of all, let's look at example 8.1 in the book. If you have a 2 kilo ohm resistor and the frequency range is 20 hertz to 20 kilohertz, find the value of capacitance needed to act as a good coupling capacitor. So here we can simply use the formula that we all learned back in University Physics 2. XC is 1 over 2 pi frequency times capacitance. So we can simply solve this for capacitance. We can plug in the information as given. XC here is 200 ohms, 20 hertz, and so we get capacitance of 39.8 microfarads. So the first place we start is talking about base biased amplifiers. In these kind of amplifiers, the capacitive reactance, XC, is much smaller than the input impedance to the base. In other words, XC is much less than 0.1 times R. So here's an example. Let's work through this. So we have the typical amplifier setup. So we can work through and find out what the base current is. It's simply VCC minus VBE over RB. Well, VBE is the voltage from base to emitter is 0.7. VCC is 10 volts. And so we can divide that by RB, which is given as 1 million ohms, and we can calculate the base current is 9.3 microamps. And in this case, we're given the beta DC. So IC is equal to beta DC times IB. So from here we can calculate the collector current, 930 microamps. Now we know the collector current, we can multiply that times the collector resistance and find the voltage from RC, 4.56 volts. So here we found IB is 9.3 microamps, and we found IC is 930 microamps. VC is VCC minus VRC. So 10 volts minus 4.56 volts, or the collector voltage is 5.44 volts. In this example, what we're doing is we're working with the information we're given and simply walking around the circuit, calculating the different voltages and currents. So what happens is once you set up the DC voltages, the whole function of an amplifier is to amplify the AC voltages and currents. So what happens here is that here you can see the base current that we just calculated, 9.3 microamps. An input AC signal simply rides up on top of that base current. Similar kind of thing with the collector current and the collector voltage. Here's another example. So coming in here, here's your AC source. This rides around 0. Well, at the base, it rides around that 0.7 volts, and here at the collector, it rides around the 5.44 volts, and this capacitor here shunts out that 5.4 volts and moves it back to 0. So the whole purpose of an amplifier, obviously, to amplify the input signal. So here, the symbol for amplification is AV, which is V out over VN. We'll use that later on. So another kind of capacitor that's used a lot in these amplifiers is what's called a bypass capacitor, XC here. So XC here is much, much less than 0.1 times R. There is another example. If you have an input frequency of 1 kilohertz, what value of C is needed to effectively short point E to ground? So this is the function of a bypass resistor, basically is to short this to ground. You get much more amplification if you can do this kind of thing. So here first we use Thevenin's theorem to find the resistance is seen by the capacitor C. That's simply R1 and R2 in parallel, 375 ohms. Then we can use the same formula to calculate what C is. Turns out that it's 4.2 microfarads. So moving on, let's talk about voltage divider biased amplifiers. So in this kind of situation, it looks a little bit different because you have a voltage divider set up, R1 and R2, feeding into the base. So you can find the voltage of the base. It's simply you can use the voltage divider rule, R2 divided by the sum R1 plus R2 times VCC. You get 4 volts for the resistance, the voltage across R2. Now you can use Kirchhoff's voltage rule. You can go start at ground, go through R2, uh, across the base emitter junction, across RE to ground. So here the only voltage you don't know is VRE, since you found VR2 from the previous slide, and VBE is 0.7, so the VRE, the voltage across RE is 3.7 volts. So these are the quantities you found already. So moving forward, you can find the IE is this VRE over RE. That's the current through the emitter resistor, 1.5 milliamps. So now we march forward. We found 3 quantities. So IC is approximately IE, which is 1.5 milliamps. So now we have these 4 quantities calculated. We can find the voltage across RC. That's IC times RC. So that's the current coming down through RC. It's 1.5 milliamps times RC. So the voltage across RC is 3.3 volts. So the whole point with this analysis, this is the DC analysis. You have to be able to do the DC analysis and figure out what the DC currents and voltages are before you can do the AC analysis. So now these are the quantities we know. So let's continue on. VCE is VCC minus RC minus VRE. So notice we're starting here at the top and we're going all the way down to ground. So you got 12 volts minus 3.3 volts minus 3.3 volts. VCE is 5.4 volts. So here's all the quantities we've been able to find so far. Our circuit. So going back now, when you apply your AC voltage on top of this, all of these voltages ride on top of what those DC voltages are. So remember, that's the purpose of C1 and C2 here. Those are coupling capacitors. And that, you get the output here coming out. So input here, output over here.